So the last topic of this chapter is acids and bases, and this is really part of discussing water because the whole reason we have to talk about that is because life is in water, and water does something a little bit strange, right? So this is water, right? And in pure water, you will always have some water do something called dissociation, and it's kind of a form of breakdown. So some of the water, a very small amount of it, will dissociate or break apart into a hydrogen ion and a hydroxide ion. I just want to remind you that water is not ionically bonded. Remember, it's made of covalent bonds. So this is not a normal state for water to just separate like sodium chloride. That's why it's called dissociation, not the breaking of ionic bonds. So the water will dissociate into an H plus and an OH. Most of the water is still in the form of H2O. A tiny amount of it has become H plus and OH minus. And specifically, this will happen to a specific concentration. And the concentration we're going to track, so there's the OH minus is in there, but we're going to keep track of the H plus. There will be 1 times 10 to the negative 7th moles per liter of H plus in that solution. Remember, that's a tiny number because this is scientific notation. 2, 3, 4, 5, 6, 7 moles per liter of hydrogen ions. Remember, moles per liter is abbreviated with a big M, and so that's where this number comes from here. So this equation is a little bit intimidating. You don't really need to worry about it for bio class. You will have to worry about it for chemistry class. But this is just telling you that the hydrogen ion concentration is 10 to the negative 7th molarity in pure water. Okay, so any glass of water is going to have this tiny amount of hydrogen ions. And so this relates to acids and bases because acids and bases are defined by what happens when you put them into water. So if I add an acid to water, I already have those H pluses there, okay? But if I add an acid, like hydrochloric acid also dissociates into a hydrogen ion and a chloride ion. So again, it's like water. It's actually made from a covalent bond, but for reasons we're not going to get into, when I add it to water, it separates into these ions. So this is creating more hydrogen ions. So this will increase my H plus concentration higher than 1 times 10 to the negative 7th. Okay, remember, this is what's pure water. This will add to the 10 to the negative 7th. A base, on the other hand, and so let me work over here, a base will decrease the hydrogen ion concentration. The way that it does this is that it takes hydrogen ions out of solution. So this is a classic base, ammonia, and ammonia will react with hydrogen ions to make NH4. So when I add ammonia to water, remember, the water has H2O in it, but it also has H plus and OH minus. And so it's these H pluses that are reacting with the ammonia and giving me NH4. So this is really, you could think of it as subtracting hydrogen ions because it's using this up. So bases will lower the hydrogen ion concentration by binding H plus. Some also release OH minus, and we're not going to talk about this because it's just beyond the time that we have to talk about acids and bases. But remember, the key is that bases lower the hydrogen concentration. You've also maybe heard of the pH scale. The pH scale is a way to measure how acidic or basic something is, and specifically a solution. So this is when you're adding acids to water or adding bases to water and you want to know what the hydrogen ion concentration becomes. The pH is really a measurement of that. So pH is equal to the negative log of the H plus concentration So this symbol just means concentration. So log, if you're not familiar with it, is basically just a mathematical manipulation. It's not adding or any other variables or anything like that. It's just taking numbers and making them either smaller or bigger so that they're easier to work with. So to give you an example, if I have 10 to the negative 7th, and I take the log of that, then it would be, well, let me go ahead and do the whole equation actually. So the negative log, which that's part of the pH equation. So if I take the negative log of 10 to the negative 7th, that's going to give me a whole number, 7. So I went from having this number that's a decimal, 0.0000001, and I'm making it into a whole number. If I took the negative log of 10 to the negative 6th, hopefully you see that that would be, negative 6 here, sorry, it's not letting me quite right, then that would be equal to 6. So it's always taking this number, and that's what the whole number becomes. So it's just turning a really awkward number to work with, 0.00001, into a whole number that's much easier for us to work with. Okay, so 10 to the negative 7th is the hydrogen ion concentration of water. So that means that the pH of pure water is 7. So this is considered neutral. Pure water has a pH of 7, and that's neutral. Anything that is lower in number, so 6, 5, 4, 3, 2, those are lower pH numbers, actually have higher H+. So it's a higher H+ concentration, a lower pH number, and that is acidic. Okay? Anything that has a higher pH has a lower hydrogen concentration, and that is alkaline or basic solutions. So if I add baking soda to water, that's going to make a basic solution. It's going to lower the hydrogen ion concentration or have a higher pH. If I add bleach to water, I have a higher pH, a lower hydrogen concentration. So that's the way that pH works. The reason why pH is important in biology is because our bodies hang out right around neutral. So again, remembering that we're all in aqueous solution, so normally our bodies should be at pH of 7. If something is wrong and there's not a pH of 7, it can have a big influence on things. So it can change the shapes of molecules, it can change how chemical reactions occur, it can change the way molecules interact with each other, it can change the way things dissolve. And so it's very important that pH be maintained in our bodies. And so remember this feature of life, homeostasis. That's when we have sort of a baseline that needs to be maintained. pH is something that has to be maintained as part of our homeostasis. And so in our blood, for example, we're going to have to keep this neutral pH. This is accomplished using buffers. So because we only tolerate small changes in pH, we need buffers to help keep a constant pH. Buffers basically they have sort of two faces. They can do two things. They can either act as an acid or a base. If the blood is too acidic, so imagine our blood is too acidic, then the buffer will act as a base. If the blood is too basic, then the buffer will, and you hopefully can guess this, will act as an acid. So the same system, buffering system, can do both. And this is just an example of the bicarbonate buffer system. This is what works in your blood. So notice these arrows going either direction. So in this direction, it's releasing hydrogen ions and therefore is acting as an acid. In this direction, it's absorbing hydrogen ions and is therefore acting as a base. So going this direction, it's acting as a base. Going this direction is acting as an acid. And that will help maintain the pH of your blood at the correct value so that your body keeps functioning properly. So we'll wrap up this discussion with a little bit of review. A solution has a pH of 2. Hopefully you know that would be acidic. Solutions of pH 10 would be basic, and pH 7 would be neutral. Remember, there's an opposite relationship, so the lowest pH value has the highest H+ concentration. And the other two I'll leave for you as practice. If you have questions about them, make sure to bring them to me in class or post about them on the discussion boards or in some way get help making sure you know how to answer them.